Well, this is a total sim video for the truck add-on predictor, which is part of the TOS Auto app. The truck add-on predictor recipe is meant to allow users to be able to design and upload their own aerodynamic devices and be able to run CFD on those devices so that they can test the overall performance of the device in tandem with the overall truck design. So what we will be providing to users is a model heavy truck design that they can then design their aerodynamic device around, and they'll be able to test the full simulation of the truck with the aerodynamic device within the TS Auto app. And so the overall goal is to reduce the drag of the truck itself. This has been something that's been going on for, say, the past 30 years, and that we've been trying to conserve fuel on the highways with our truck designs. And so you'll see things like skirts and streamlined cabins and sealed gaps between the truck and the trailer. And so what we want to do is allow users to be able to quickly iterate over their designs through the app so that they can figure out what the overall drag coefficient of their device is and what effect it has on the overall drag coefficient of the vehicle, because there's a lot of airflow dynamics that are going on that won't be able to be fully realized unless you're testing the device with the truck itself. And so instead of having to go to a wind tunnel, we allow you to run those CFD simulations through the app itself. And so it only takes a few minutes to get things up and running. The truck add-on predictor recipe is providing two different recipes for the users. There is the steady RANS model and the DES transient model. The steady RANS model is computationally inexpensive and can solve relatively quickly within, say, around 20 hours, whereas the DES transient can take up to more than 2 to 3 days of solving. And so it's much more computationally expensive, and therefore the simulation cost itself costs more as well. And what we've found is that the DES transient case is a bit more accurate in terms of predicting the drag coefficient of the vehicle. If we look at this graph here, you can see that the blue experimental data more closely matches the curve of the DES transient data, whereas the RANS steady data doesn't necessarily match as well. And so what we recommend to users is that they run the steady RANS model first and use that to iterate through designs. And then we recommend for a final validation to use the transient model to perform the final validation. And the other thing we recommend is that you perform several iteration points of the wind speed yaw when running the test of each design. And so what that means is I'll run a simulation at 0 degrees yaw, which is to say that the wind is impacting the vehicle directly at 0 degrees. And then I'll run several more simulations at, say, 1, 2.5, and 5 degrees yaw. And then once I've gotten a series of points at different yaw angles of the wind, I can then use a cubic spline to get the final average, the wind averaged drag coefficient, which is meant to more model the effect of the changing wind on the vehicle. Because when you're traveling on the highway, you can expect the wind that the vehicle is facing against is going to be changing in direction. So this is the wind averaged drag coefficient that we recommend trying to accomplish. And we'll provide an example Excel for how to use those points and get the final drag coefficient value. Of course, you can always just run your simulations at 0 degrees yaw and use those drag coefficients to just compare one design from the other. But when you're wanting to compare your results versus experimental results or versus scientific literature, we'd recommend using an averaged drag coefficient with different yaw angles and that'll help you get closer to the experimental side of things. Now, when you're actually using the app for the truck recipe, it's relatively simple. What you'll first do is you're going to create your program, and your program is just a way of organizing your projects. And so we'll just call this truck program, and we'll select the truck tool and click save, and then we'll go into this program, and then we'll make a project. And typically what you do is you'll have a project for a month's work, or if you're testing 2 different vehicles or something like that. In our case, since we're just testing multiple like boat tails of a truck, we're just going to have a single project. So we'll call this boat tail 01. And then we'll go into the project. And then what we'll need to do is just go to geometries and go to parts, and then we're going to upload parts. And so now that we're on the parts and assemblies page, all we have to do is go and upload a part. And so we'll go into temp directory and then grab some flat side boat tail panels, and then we'll select meters as the units, and I'll select tail part as the geometry type, and we're going to click submit. And so now we have this part. I don't need any assemblies because all I have to really do is upload a single part. Assemblies is meant for more complicated geometry for different recipes, but for the truck recipe I would recommend just not even worrying about it. And so we can just double check the bounds. Yeah, that's proper scaling in meters, and the name is fine. I'll click save, and if I want I can inspect it in the 3D view. Yep, that looks right. Go back to geometries, and there's 2 ways of creating simulations. There's the parametric sweep and the new run. If you do parametric sweep, click new sweep. I'll call this run 001. Select the truck add-on recipe, and this is the steady RANds model that it's using. And if I then go to select the model, click save, and let's see, and I'm going to do a 0 yaw with around 65 miles per hour, which in meters per second is around 29, I think. So then we'll test also at 2 yaw, and we'll also test at 5 yaw. Right, so now I have these 3 yaws. They're all going to use the same speed at 29 meters per second. And then I'm going to click save again. And so now it's generating 3 runs for me. And the first run is going to be 20 tokens, and then these next 2 runs, because they're sweep runs in terms of the fact that they use the same geometry, and that their only difference is that they have a different yaw angle. And so that's really it. I've selected my part, I've set the yaw and the velocity, and then all I have to do is either click submit all, or I can submit one after the other like so. And now I have these 3 simulations queued. If I click on reload job state, it should show that this one's queued now and that these 2 are held, in terms of the fact that they are held or waiting for this one to finish, and then this one will run, and then this one will run. And so that will then reduce my tokens from 100 to 66 tokens. And if I go to new run, this is another way of just making a simulation. I can do run 02, and then I can just manually set the yaw here, 29 meters per second. I can choose whether or not to include the skirt as well. So if I set the skirt to off, then the truck won't have the skirt as part of the simulation, but if I have it on, then it will have the skirt as part of the simulation. And I'll select the geometry again and click save. Now, one of the other things you can do is you can check your 3D view again as well, and it actually will try to load the truck itself. Now, the truck is rather big, so even with my rather fast internet, it's loading rather slowly. So I would just really confirm that your add-on device is flush with the truck, and then once you know it's like this, then you can go ahead and close out. We do provide this that static truck geometry on the documentation site, which you can access through this docs site here, and then just search truck, and we have the truck geometry as part of a Google Drive folder. Anyway, so then I can click submit. It's going to cost me 20 tokens, and so I'll submit. And so yeah, so now I'm back from 66 to 46 tokens now is my balance, and this job is queued as well. Now I'm going to go ahead and delete these simulations, and I'm going to show you guys some results as well. So here we can see some of the results of the truck simulation. What you'll get is you'll have some curves of the drag and the downforce, or lift in this case, and this will kind of let us know how the convergence of the results looks. So we can kind of see how it slowly converges over each iteration of the simulation. We can see the total forces as well as the final drag coefficient and the individual force groups of the truck. And there's also images, so like images page, and view the results of the images, and there's also movies as well. And so that essentially covers it. For the most part, all you're really going to care about is the drag coefficient of the truck, and there's also a 3D results viewer of the data as well. So that's it. Thanks for watching the truck add-on predictor recipe video.